at rest produces only an electric field, and the charge in motion produces both an electric field and a magnetic field. Let us place a source charge Q at a point in a vacuum. The space around the charge, when it can influence other charges, is called its electric field. Now, let us place a small test charge Q is placed at point S in the electric field at a distance r from the source charge Q. Then, the intensity of the electric field at the given point S is defined as the force per unit charge. According to Coulomb's inverse square law, the force between the two charges is F is equal to QQR cap divided by 4 pi epsilon naught r square. Let us label this as equation 1, where r cap is the unit vector along the force vector and epsilon naught is the permittivity of the free space or air. Then, the intensity of the electric field at point S is denoted by E is equal to F divided by Q. Let us label this as equation 2. Substituting equation 2 in 1, we get the intensity of the electric field as E is equal to QR cap divided by 4 pi epsilon naught r square, where r cap is the unit vector along the electric field vector. The electric field has its own existence and it's present even if there is no additional charge to experience the force. Thus, the field due to Q exists even in the absence of the additional charge Q. The field can convey energy and momentum and takes a finite amount of time to propagate. Thus, if the charge is displayed from its position, then the field at a distance r will change after a time t is equal to r divided by c, where c is the speed of light. Note, we will assume that the field due to a charge at a given point does not change with time at a given place. If there is more than one charge in the space under consideration, the electric field at a particular point is due to more charges. Consider three charged spheres with charges Q1, Q2, and Q3 placed at different locations as shown. Then, the fields due to all the charges should act vectorially. This is called the principle of superposition. If E1, E2, and E3 are electric fields due to charges Q1, Q2, and Q3 respectively at point S, the resultant electric field at point S is E1 plus E2 plus E3. This is with regards to charged bodies or charges at rest. Let us now learn about charges in motion. If a charge Q is placed near a current-carrying conductor at point S, it does not experience any force because there is no electric field at point S. This is due to the fact that the conducting wire contains an equal number of positive and negative charges. It is electrically neutral and hence does not produce a net electric field. If the charge Q is projected from point S in the interaction of the current in the wire, the charge gets deflected towards the wire if the charge is positive and away from the wire if it is negative. If the charge Q is projected from point S in the opposite direction to the current of the wire, the charge gets deflected away from the wire if the charge is positive and towards the wire if it is negative. From these observations, It is clear that there must be another field other than the electric field that exerts the force on the charged particle Q. This new field exerts a force on the charged Q when it is moving. This new field is the magnetic field created by charge Q when it is in motion. Magnetic field is denoted by the letter B. The current in the wire is nothing but charges in motion. Thus, there is a magnetic field due to the current, and this magnetic field interacts with the magnetic field due to the moving charge Q. The interaction between these two magnetic fields causes the charge Q to deviate from its path. Thus, the moving charges produce both an electric field and a magnetic field.